Welcome back, everyone, to this morning session. So the first talk will be by Krishnendu Sengupta from IACS Kolkata, and he will be talking about aspects of Hilbert space fragmentation.
Okay. Good morning, everybody. And I'd like to begin by thanking the organizers for inviting me here. And so the topic of the talk today is some aspects of Hilbert space fragmentation. And we have been working on this phenomenon for quite some time. What I'm going to talk about today is the possibility of a prethermal realization of Hilbert space fragmentation in a fluke-driven system. So, and also, if time permits, I would like to show how this phenomenon could lead to reality of eigenspectrum in a non-Hermitian model. That's not dynamics, but that would be sort of a different thing. So these two works are done with Shomshubro Ghosh, who is a student of mine in IACS, Kolkata, where I work, and Indranil Paul, who is a longtime friend and collaborator from Paris. There are some other works which I'm not going to talk about, and these are done with Bhaskar Mukherjee, who is currently in the audience, Swannesha, who is now a faculty at Belur, Ramakrishna Mission, and Arnab, who was here till yesterday, okay, my colleague at IACS. So here is a brief outline of the talk. So I'm going to sort of skip the first part mostly because there have been too many talks, well, a lot of talks on Hilbert space, this Eigenstate thermalization hypothesis. So the audience is already familiar with this. And then I'm going to briefly introduce Hilbert space fragmentation, which would be necessary for the second, these parts of the talk. So after that, I'm going to show that a driven Fermi chain can show fluke signatures of Hilbert space fragmentation in a prethermal sense. That is, there is a window of time or number of drive cycles where the response on several things, such as entanglement, entropy, or autocorrelation function of this driven Fermi chain will mimic that of a system with Hilbert space fragmentation. Okay. Of course, this doesn't continue forever. I mean, depending on what your drive amplitude or frequency is, this will ultimately go away. But for a finite change, it can take a very long time scale, and that time scale is exponential. So yeah, so this prethermal regime can be quite long. Okay, if time permits, after this, I'm going to come to this non-Hermitian quantum model, called the Nelson-Hatano model, and show this model has a phenomenon so this is a model of fermions hopping on a lattice with some nearest neighbor interaction, but the hopping of the fermion is non-reciprocal. That is, the right hop and the left hop have different strength, and that's what makes the model non-Hermitian. Thing in the model that if you increase your interaction strength to a number greater than a critical number, what happens is that the entire eigenspectrum of this model, in spite of this being a non-Hermitian system, becomes completely real. And this is a effect for finite size system. This doesn't have a thermodynamic limit because this critical strength just diverges as you take L tending to infinity limit. But what we would like to show is that this Hilbert space fragmentation might give us a way of understanding why this happens. Okay. So let me just begin. So, okay, so this is taken from Anatoli's review, so the idea is that when we consider a generic state of a quantum many-body system, I can write this state in its eigenbasis, and then if I try to look at the time evolution of a generic operator, I get this answer. So, and when you stare at it for some time, you see that there is these issues with long time behavior. So if I first say that, okay, I'm at long enough time and I've reached a steady state, you see in this steady state, I retain memory of the initial condition because the mod CM square is still there. And this does not agree with the standard microcanonical ensemble prediction. And also there is this other thing that it takes an incredibly long time to reach the steady state because the steady state is reached when the time is larger than inverse of this gap. And as we know in a typical ergodic many-body system, this gap in the middle of the spectrum is exponentially small in system size. So this tells you that you take literally forever to reach the steady state, and that's not what we see in the experiment. The point to be noted is that invoking random matrix theory remedies these problems, because with random matrix theory gives the following structure to the expectation value of this of typical local operators, so that OMM is O prime, that's a constant, which means that this dependence on the CM square goes away. So, and OMN is 0. However, it doesn't provide an energy dependent answer, which is typically seen in experiment. And that's what ETH seeks to remedy, essentially. So it says that the matrix element will be some O, which depends on this E average, which is the energy of this eigenstate M, and an off-diagonal piece which would be exponentially suppressed by this entropy. Okay, so and I'm not going to get into the details, but this has been incredibly successful for explaining many different phenomena. And but what I'm going to say is that, okay, so one thing that this ETH requires is ergodicity. And whenever this ergodicity is violated in different ways, you see deviation from this ETH predicted results. So for example, if you have integrable models, because there is a large number of conserved quantities, you would see that there is loss of ergodicity, and this prevents realization of long-time thermal steady state. Many-body localization, if it exists, is another example, and I'm not going to talk about this too. Also, there is a weak violation of ETH, which can happen due to presence of a special class of eigenstates in the Hilbert space, which are called quantum scars. But this is weak in the sense that you are going to see this effect only if you start looking at operators or start from initial states which have which has large overlap with this scarce subspace, because it's a small subspace in your Hilbert space which has this special eigenstates. So, but if you start from a different state which doesn't have an overlap with this scarce state, you don't see this at all, and ETH prevails. Okay, so in that sense, it's a weak violation. I'm going to mostly talk about this violation of ETH due to fragmentation of Hilbert space, leading to loss of ergodicity, and this is typically known as strong Hilbert space fragmentation. And the idea of the talk is to find out a prethermal realization of the strong Hilbert space fragmentation. And whatever I have said also holds in a slightly modified form for periodically driven system, because you when you drive periodically, instead of the standard ETH, you go to this quote-unquote infinite temperature ensemble. It's really a circular orthogonal ensemble with eigenvalues of U on a circle, which is equally spaced. And this leads to a featureless long-time state. However, there can be prethermal regimes where things can be more interesting, okay, in many cases, and that's what I'm going to talk about. So let me begin with essentially some aspects of Hilbert space fragmentation, and I'm going to, so what is this? This is essentially breakdown of Hilbert space into an exponentially large number of dynamically disconnected sectors. So if you write this in a computational basis, we're going to see that there is no matrix element of Hamiltonian between these blocks, so to speak. And such a separation of Hilbert space is different from that due to global symmetries, because it's exponential. For symmetries, it scales algebraically with the system size. Now, the way to figure out about the strong Hilbert space fragmentation is that if small n is the dimension of the largest fragment and capital N is the Hilbert space dimension of the total system, n by n should go as exponential of minus L in the large L limit, which tells you that there must be exponentially many sectors. And there are many models which exhibit strong Hilbert space fragmentation. Most of these are 1D, but there have been some two-dimensional models and higher dimensional models which have been put forth recently. One of these is this work with Arnab. So what are the signatures of this strong Hilbert space fragmentation? How do you see this in an experiment? Well, one of them is this issue. In this kind of setting, if you calculate the autocorrelation function, you are going to see that it doesn't go to 0 in the long time limit. There is a memory retainment. And this has to do with something called a Mazur bound, but I'm not going to get into the technical details of that. But it's known that this autocorrelation function has to be larger than a lower bound. And the other thing is that there is deviation of entanglement entropy from its symmetry resolved page value. And that's because if you pick up a state at random and say you drive it, it will go to the page value of the fragment, and not the page value of the entire system, because it simply doesn't see the system. Okay, it under evolution of the Hamiltonian. Okay. So here is a model which will be important for later. So this is a model with correlated hopping, and this just says that hopping can only take place if you don't change the number of bonds, which as fermions are occupied at both ends. Okay, so this is what this projection implements. And the conservation here is the fermionic charge and the number of bonds because of this hopping. And for later, let me just define. So if I have two occupied particles, so if I have a Fock state with these two occupied particles, side by side, I'm going to call it a particle defect, and similarly hole defects out here, two empty sites. And one particle and one hole defect would be called a particle hole pair. This is going to become important for later, so I'm just going to introduce it right now. So here you see, this is an example of a Fock state, which doesn't connect to anything, and it's eigenstate of this Hamiltonian with eigenvalue 0. So essentially, here, none of the fermions or holes can ever hop. Okay, so these are called frozen states, and there are exponentially many of them. But there could be other things within the half-filled sector, different sectors, which are not connected to these frozen states. So the number of particles and hole defects in this model are separately conserved, and also the parity of the starting defect sites are conserved. Okay, so it can be even or odd, but they don't change under. So there is a counting of fragmentation, and I'm going to go through it quickly. So how do we count? How do we actually show that we have this exponential so we have this fragmentation. To do this, first let's count the number of states in the largest symmetry sector, which is the half-filled sector. And this has L/2 particles and L/4 bonds, which has, for a chain of length L, which has fermions at both ends. So how do we count this? So what we do is that we first fill these L/2 sites with particles, but now we keep L/2 bonds. So this, is just a configuration like this. Next, but we don't want L/2 bonds, right? We want L/4 of those. So what we do is that we insert holes, sites, empty sites, so that we break L/4 of these bonds. Okay. So see, this bond is now broken. Okay. So this bond is now broken, and that. So this can be done in L/2C, L/4 ways, pretty easy counting. And then the next one is to insert L/4 more empty sites, because in total we need L/2 particles and sites, empty sites for half filling, and without breaking any bonds. Okay, and this is a combinatorics problem, and the answer to this is that it can be done in L/2 minus 1C L/4 ways. It's called the classic ball and bar problem, if that rings a bell. So essentially, and finally, there is a factor of 2, because what I call particle, I could have called holes and vice versa. And therefore, this gives a factor of 2 to the power L/L. Okay, so that's the dimension of the largest symmetry sector. But now let's come to the dimension of the largest fragment within the symmetry sector, which contains, again, it's at half filling, and it has L/4 particle defects, which for a site of 12 is this thing. So I have 1, 2, and 3 particle defects, which are next to each other. And L/4 hole defects, they should be equal. And the rest, P, particle hole pairs. Okay. Now I start with a configuration like this, and under action of the Hamiltonian, what can happen is that these particle hole pairs can diffuse inside this structure. Okay. And essentially, you see that from here, this particular hole can hop to one side in the right, and this is like this particle hole thing has gone by one side to the left. Okay. So this is the way this diffusion happens of these particle hole pairs into this. But now you ask the question that how many possible configurations can I have? And the answer to this is again that you need to sort of distribute this number of P pairs, these particle hole pairs, among 2ND empty sites, where ND is this particle defects, okay, which is essentially the number of empty spaces between particle hole defects. And this is again a classic combinatoric problem, which is an answer. And the answer to this is just this, okay, it is factorial. So you count this, and then you divide this by the total number of states in the Hilbert space in this symmetry sector, and you see that it's exponential. Okay. So essentially, this gives you this fragmentation. Okay. Not any state to any state. So this is a fragment in the sector. You can go any state to any state within a fragment. But the symmetry sector is much larger. It has many different fragments. Okay. Okay, so now let me come to, yeah, sure.
Yeah, this is largely just a question about terminology. So is this exponential number of fragments a key part of what makes the presence of some conserved quantities Hilbert space fragmentation as opposed to just a conservation
law? There is no per se conserved quantities here except for this charge and number of this thing. There are some statistically localized integrals of motion, something called SLIOM, which this Frank Polman and others have got into. That won't be important for these talks, but apart from that, I really don't know of conserved quantities in the sense of integrability. Okay.
So there's some other mechanism of having different Hilbert space sectors? Then?
No, there is this constraint, and this constraint just breaks the Hamiltonian, the Hilbert space into different sectors. Okay. Now, whether or not you can characterize them by a conserved quantity, the answer is I don't really know, except for this statistic, this SLIOMs, the statistically localized. I don't know of any other thing which can do that. But it's not very important for this purpose. I mean, so yeah. Okay. Okay, so let me now see if I can have a prethermal signature of this strong Hilbert space fragmentation. So what we do here is we take a Fermion chain. It's just a chain with nearest neighbor and the next nearest neighbor interaction. And the next nearest neighbor is put in just to make it non-integrable. It's not really necessary for our purpose, but we'll do it anyway. And then we drive the interaction term. Okay, so that's the protocol. I can do this by a square pulse protocol or a cosine protocol. And one aspect of this would be computation of this numerically, which is done by exact diagonalization. And for example, if I am using a square pulse protocol, I'm just going to do this. So I know what my evolution operator is. So as long as I know the eigenstate and eigenfunctions of H plus and H minus, which corresponds to V of t as plus or minus V1, I can express my US, this U corresponding to the square pulse protocol, diagonalize this, and then get the Fluke Hamiltonian from there. But if I am doing a continuous time protocol, I have to work a little bit more because I have to do this Suzuki-Trotter decomposition into finite small time steps and do the same thing. So, and also for perturbative analytics, I'm going to use what we call as Fluke perturbation theory. This is really a rotating wave approximation plus Magnus if your drive time is the largest term in the problem. And there is a way of doing this, but the point is that this is again something very standard. It's just standard perturbation theory, time-dependent perturbation theory, except for the fact that this U naught now has a time-dependent Hamiltonian. That's the only modification. Okay. So now, let me take this driven Fermi chain and to begin with, be in the high drive amplitude regime and find out this Fluke Hamiltonian using this Fluke perturbation theory. Okay. So this is just the first order Fluke Hamiltonian using this Fluke perturbation theory. So if you look into this, if you look into this Hamiltonian, you see that the terms which depends on n, that essentially commutes with this piece, and therefore, they are not going to change much when it comes to the first order Fluke theory. But this hopping term is going to change, and the way it changes is that now the first order Fluke Hamiltonian has two types of hopping. One in which you conserve this number, okay, the same projection operator that you had for the chain, and the other one where you don't conserve it. Okay, so if aj square is equal to 0, which means that the j plus 2th and the j minus 1th side have the same occupation, then the hopping proceeds via this term, and if not, if it is 1, then the hopping proceeds via this particular second term. Okay. And there are explicit analytical expression for both of these. So the point is that now you can see where I'm going with this. So there are special frequencies. So this gamma naught is a combination of the drive amplitude and the drive frequency. And therefore, there are special frequencies at which this f gamma naught vanishes, and the first order Fluke Hamiltonian becomes becomes identical to the chain with this projection correlated hopping. Okay, there are of course this HF, there are these diagonal terms, but that doesn't do anything to your fragmentation structure, and therefore this first order Fluke Hamiltonian gives fragmentation. But of course, this doesn't mean that your driven system is going to show fragmentation, because there are higher order terms. However, for large drive amplitude, such terms are small, so one expects at least a prethermal regime, where you are going to see this. And we are going to see what the details are. But the point is that we did work out the second order Fluke Hamiltonian, and that doesn't respect this fragmented structure for any frequency. Okay, so there is a correction there. Okay, so the first signature. So now I'm going to do exact numerics. And then, so at the first, I'm going to look at entanglement entropy. So here, what we do, we pick up a random state from the Fock space, drive it, and see what happens to its entanglement as I go a function of a number of drive cycles. So if I'm away from this special frequency, the entanglement just goes to the page value, which is what is expected in a driven system. If I am at the special frequencies for low drive amplitude, it still goes to the page value. But as I increase my drive amplitude, it goes to the page value of the fragment from which I have drawn this. And in this case, it is drawn from the largest fragment, whose Hilbert space dimension is roughly, okay, log of the Hilbert space dimension is roughly 0.8 times the entire stuff. So it just goes to the page value of this of the fragment. Okay, and then if you now keep picking states at random from different fragments and you drive them, you see that in the large drive amplitude regime, each of these goes to a different value, which essentially tells you that the entanglement is seeing different fragments. Okay. So this entanglement entropy saturates to an initial state dependent value for this different this thing, which is a signature of this prethermal Hilbert space fragmentation. Okay, the other thing one can do is this autocorrelation function. And here also you see that this autocorrelation function, when you drive it, it goes to a, it basically goes to a finite value. It doesn't go to 0 if you are driving it at special frequency and with large drive amplitude. So here there is a thing that I would like to point out, that if I look at the value, this late time value of this autocorrelation function as a function of V1, I find that there is a semi-sharp rise as I cross a threshold. And however, as I increase my system size, this rise kind of drops. And so this is a finite. So in this sense, I would think that the value of V1 would increase with system size, although our numerics haven't, to the extent that we could do this, we haven't been able to figure this out completely. And so here is a phase diagram which plots this value of the autocorrelation, late time autocorrelation function. And you see that at these special frequencies out here and there are these large values of this late time value of the autocorrelation function. Okay, so near the threshold value, the extent of the prethermal regime, which is this plot, grows exponentially with the drive amplitude. Also, and this is an exponential scale, and as I go deep inside this, this becomes unmanageable numerically. So, but near this threshold, we could find this curve. So this is a prethermal this thing. The other interesting thing that happens here is that we are calculating this equal time correlation function of density correlation function of these fermions. So if I am driving this system with this special frequency, what we find is that for a generic Fock state, this just shows some tiny oscillation, never goes to the typical value. This red is when I drive it away from the special frequency, and blue is when I drive it at the special frequency, and so there is a difference. But most interestingly, when I start from this up-down states, this Z2 state, which has particle hole kind of thing, there is a oscillation. So what this oscillation requires, in addition to having this Hilbert space fragmentation, is a Z2 symmetry. Because so first, let the Z2 state in our language is a state with number of ND equal to 0, which are eigenstates of HF1 with some same quasi-energy. So, these are Z2 and Z2 bar states. Now, in addition, it also requires fragmentation. So that starting from the Z2 state, I just don't spread away in the Hilbert space. And numerically, we find that in our dynamics, the significant contribution comes from states with ND equal to 1. So it's a picture like this. So what this does, in effect, is to generate a tunneling between this Z2 and Z2 bar, and they split the energy of the antibonding and the bonding orbital. And that's what sets the scales of this frequency. And this, since it happens with multiple tunneling, this scale is quite long. So the time period is quite long. And this is the oscillation that you see. You also see that if we are doing this at low drive amplitude, this oscillation persists for some time and then just dies, okay, because the system keeps spreading. So the dynamics of this Prosen state, this has no analog in standard Hilbert space fragmentation, but this is a prethermal Hilbert space fragmentation which has this signature. So now I'm going to go to out of time correlators. How much time? Okay, good. Thanks. So I'm going to go to this out of time correlator stuff. So as we know that this is this square of the commutator, okay, and I'm going to take this density as the operator. And this can be written as 2 times 1 minus Fm, F, where M is the number of drive cycles here. Sorry for change of notation. And this is given by this particular function. So, and it's known that, if you have an ergodic system and F shows that F it converges to its steady state value, which is F equal to 1, and then this correlator goes to 0. So here, what we see, and this is work still in progress, we don't have the full data here. And this is really for small system size. I don't have the data for higher system size yet. But I just wanted to show you that if you are driving away from the special frequency, F goes to 0 pretty fast, where at special frequency, this is not so fast. And if I just plot the number of drive cycles after which F reaches this near 0 value on the farthest side of the chain, that thing at the special frequency grows with this drive amplitude. Saying that, again, you are getting into a regime where there is prethermal fragmentation of some sort, or at least prethermal loss of ergodicity. Okay, so this is what I wanted to talk about in terms of this prethermal realization of Hilbert space fragmentation. So if you have any question regarding that, I can take this now before going to the next topic. Yeah. The Mazur bound.
Yeah, the Mazur bound, and so that's
Yeah,
related to the integrals, right?
So here what happens is that, I don't have conserved quantities, right? But there is this paper by Frank Polman and others who basically said that there is some statistically localized integrals of motion. So if you take a typical state and take some operators and take their expectation value, they remain conserved. And using those statistically localized integrals of motion, you could do a Mazur bound type calculation. And this is consistent with this. That much I have checked. But quite frankly, I'm not entirely happy with that calculation. So let me just put it better. So that's why I didn't put it up out here. Any other? Yeah, please. The mic.
Any Hilbert space fragmentation model, can you design a Floquet protocol that will have that as the first order Floquet Hamiltonian?
So the idea here is to sort of generate a first order Floquet in a driven system. So this really depends on the model. So one is to, so this is not a model independent statement. Mm-hmm. So if you give me the model, I can tell you yes or no.
But in general, it's not. There's no recipe to create given any Hamiltonian.
Probably not, I would say, because well, I can at least think of some models where I don't know how to do this. So I would. We can discuss after. I mean, this will recur a blackboard actually. Yeah. Okay. So, any other? Okay, if not, let me just move on, and I'm going to be a bit quick with this. 5 minutes, 6 minutes. Okay, sorry. Yeah, no, I am not going to argue with the chair. So, okay. So there is this non-Hermitian quantum systems, and it is expected that a generic non-Hermitian quantum system would yield complex eigenvalues. But the question is there a sufficient condition which guarantees the reality of its eigenspectra? And the typical answer that you would find in the community is PT symmetry. But I would just like to point out that these global symmetries, they are not enough because they ensure that the eigenvalues are either real or comes in complex pairs. And usually they don't make a statement apart from other details being fed in, which one of them is realized. Okay. And so to answer this question, we study this finite Nelson-Hatano chain at half filling and try to provide an answer to this question, at least for this model. Okay. And we have checked this for other models, it works, but I'm going to only talk about this currently. Okay. And for other models, please refer to the reference, this paper that we talked about. So the global symmetry at half filling are the following. So you have a parity and a particle hull which takes H to its dagger. And then there is translation, and this PC together commutes with H. So this model essentially also has a Hilbert space fragmented regime for very large V, because you see, once I take this large V limit and I just sort of get the effective Hamiltonian, I'm going to generate this projected Hamiltonian that I talk about, with the difference that now the hoppings are not reciprocal. But reciprocity of hopping is not a requirement for Hilbert space fragmentation, and the model still shows Hilbert space fragmentation. Okay. So also I would like to point out, because I'm running out of time very quickly, that what happens in this model is that beyond a critical V1C, which depends on the length of the chain, and this V1C doesn't have a good thermodynamic limit, it just goes to infinity as you change L, all the eigenspectrum, they become real. Okay, and then out here there is one exceptional point which makes two of these eigen values complex, and then there are more exceptional points, and therefore the maximum of imaginary part of epsilon just keeps on jumping. So this is the structure, and this V1, so this V1C depends on gamma, and also you can see these exceptional points being developing here in some. So let me move on. So to understand what happens here, let me sort of now take the Fox states of this model, and then just label these states by the position of the particle and hole defect. So I have a particle defect here, which means that I'm going to say this is 5, and a hole defect here, which means I'm going to say this is 7. That's the initial site at which this defect is. And then due to half filling, there are equal number of particle and hole defects. Moreover, there is this thing that two adjacent particles and hole defects are always going to be an even odd or odd even sites, and two adjacent particles and two adjacent hole defects, they are going to be an odd or uneven. So see here, there are two adjacent particle defects. So if this is 2, and that should be 3, so you have a 2-3 combination, and similarly for the others. Okay. So the action of the Hamiltonian, which changes the position of this defect, can be viewed as a many-body hopping problem in Fock space here. Okay. And that's the point that I want to make. So the other thing which is interesting in this limit, the defects cannot move through each other, and their number ND and their parity of site coordinates are conserved in this limit of Hilbert space fragmented case. So the positions of the defect changes by 2 modulo L. Okay, so now what I'm going to tell you is that this many-body hopping problem is an example of a geometry with periodic boundary condition, because starting from any state in any fragment, you can have several hops in Fock space and then come back to the same problem. And what I'm going to claim is that for all closed loop in this fragmented limit, there are equal number of right and left hops. So I'm running out of time, so I'm just going to quickly give you a flavor why that is the case and why that is important. So just think of this possibility, what can happen when I do these hoppings, these defects basically move. One possibility is that these defects go up to a certain length and then retrace their path. But once they do that, if they move, say, 3 spaces to the right and then 3 spaces to the left, there are an equal number of right and left hops. Okay. The other thing that can happen is that the defects move across the chain and they get back to their original position using the periodic boundary condition. But this can only happen if other defects perform the same circular motion, because defects cannot go through each other in this fragmented limit. So as a result, there are again equal number of right and left hops. There are more complicated cases, but we have checked this, and most of them, they have equal number of this, and all of them actually, they have this equal number of right and left hops. So now, why is this important? Once you have this equal number of right and left hops, it turns out that you can design, even in a periodic geometry, a many-body similarity transformation, which is going to make the effective Hamiltonian Hermitian. Okay. This similarity transformation is known in real space and in open boundary condition. But this extra criteria that you have the equal number of right and left hops allows us to do this similarity transformation even in a periodic geometry. So this is a many-body similarity transformation, and therefore in the fragmented limit, we have this reality of this eigenspectrum. Just 1 minute. Yeah, I have 2 more slides, so I'm just going to, yeah, thanks. But then if you lower the interaction strength, it turns out, so I'm not going to get into the details of this. This global symmetries essentially protects this reality up to a finite V, after which an exceptional point develops and you lose this total reality of eigenspectrum. An interesting outcome of this is that if you measure any correlation function of this model, okay, and try to figure out the time it takes to reach the steady state, that's going to show a huge peak at the point where the first exceptional point appear. And the reason of this is very simple. At the right of this, you have all real eigenspectrum. So, it's more or less like an ETH. So there would be a thermalization time to reach the steady state. At the left of this, the imaginary part of these eigenvalues have grown quite a bit. Okay. And therefore, the steady state is reached very fast. But here, there is this, this single small imaginary part of one eigenstate, which is going to give you a very long time to reach the steady state. That's what happens, when you look at this correlation function. So the time taken by the equal time correlation to reach the steady state diverges at the first exceptional point, and that divergence can be picked up in this kind of measurements. So I think I'm going to stop here. I hurried through the last part a bit, but hopefully, this turns out to be a mechanism for generating real eigenvalues in a many-body non-Hermitian system. And we have checked this with other models, and there are at least 2 other models where these things work. And so, although we do not have a model-independent general prediction, but it seems that at least for some models, this is going to work. So I'm going to stop here, and thank you for your attention. The chair is already staring at me. So, yeah, thanks.
Thank you very much, Krishnendu.
Yeah.
So at this real transition for the
you mean this
the levels, what happens to the levels? Do they go from, I mean, if it's fragmented?
So if you have no, it's not fragmented anymore at here because I have lowered V. See, this transition takes place at some V1, critical. That's not the infinite V limit. Okay. So what I'm saying is that the infinite V limit, because of this fragmentation, all the eigenspectrum are real. Then if I lower this up to a point, this global symmetries protects that reality. But out here at V1 critical, you are not in the fragmented limit anymore, But then these 2 eigenstates come and coalesce, and they go out with having this complex this thing.
But even in the complex part, I mean, it could have sort of random matrix.
Yeah, of course.
While in the real part, because of the, I mean, if there's a continuous connection to the fragmented limit.
There is no content. It goes through an exceptional point. That's like a critical.
No, but there is no there's a phase of the fragment. You're saying there is a fragmented phase,
so if you look at the, there is a phase, of course. So that's the diagram.
So if there's a fragmented phase.
No, it's not a fragmented phase. Out here, the system is not fragmented. Fragmented limit is for V1 tending to infinity. Out here, there is this fragmentation, but I mean, there is this.
So in that limit, there is no fragmentation in
throughout. No, there is no fragmentation, but the eigenspectrum still remains real.
I see.
Okay. Yeah.
So it'll be, your prediction is it'll be GOE in that phase.
It will be close to, yeah, I would think so. This is something we need to check. I haven't checked this, but I would think so, because everything is real, although there is this issue of this left and right eigenstates and stuff like that. So, but the level statistics, at least I would think would be something similar. Other things which involves eigenfunctions, I don't really know. I have to check.
And on the left of that, there'll be like non-Hermitian.
Here it's a
randomized.
Ginebra, I would think. I mean,
Yeah.
that's a standard.
Okay. Thank you.
Yeah.
Yeah,
Manish.
when you said that for other models also it will work, did you mean the ones with this kind of hopping non-hermiticity?
Okay,
Because
one of them is an hopping, which is just the SSH generalization of this that works. The other one is a 3-spin model which shows this fragmentation in the large thing limit that we have checked. That also works apparently.
But if you have like on-site non-hermiticity, then the spectra is complex on both places.
No. So that's the point. But those kind of things, the first thing to check is whether they have a fragmented limit or not.
Oh, okay.
Not all models do have fragmented limit, and then it's not going to work. Okay.
Any other questions?
Yeah, Anatoli.
I'm really curious on the level of matrix. Can you see this similarity transformation that it works? Because you gave some argument, which of course it was physical. I can follow it, but
yeah, in the level of matrix.
You just if you have like small dimensional matrix, like
yes, there is a thing written in our paper, that similarity transformation matrix. The whole thing is written down,
and you can see it sort of by your eyes. So you really need this physics intuition.
Yeah, this was complicated. I always refrain from giving this talk because there is so many things in the background that is really difficult. But Somsubra did a wonderful job with that actually. He actually found out that matrix and it was really nice.
No other questions, then let's thank Krishnendu for the very nice talk.
Thank you.
And